Okay, so welcome everybody to this class, commutator class about commutation and heaps of pieces. Happy New Year to everybody. So it's a kind of part of a enumerative, algebraic, and bijective approach to combinatorics. And there will be some interaction between physics, mathematics, and computer science. And the main topics is this two commutation and heaps of pieces. So chapter 1, what is a heaps of pieces and what is a commutation? So chapter 1 will be basic definition. So first, what is a commutation node? So I will start slowly. Everybody knows this identity, but maybe it is not true. Because if AB is different from BA, then you have this identity. So we take some letters, some variable, A, B, C, D, and maybe I don't have the mouse now. So we have formal variable, A, B, C, D. Some variable commute, A, B equal BA or CD equal BC, and some variable does not commute. So we have a kind of binary relation, we have a kind of graph. We have two graphs, in green and in red. The graph, the vertices are the letters A, B, C, D. So the non-commutation relation, we have some edges between two vertices B and C, for example, they don't commute, which commute. And in red, we have the non-commutation relation if the variable does not commute. So to give a set of commutation, we can give a graph on binary relation. Now if you take any variable, like A, B, C, A, D, then you can apply the commutation relation. For example, if I apply to BC, BC equals CD, so I can commute B and C. Or I can apply this to AD, and I can commute A and D and get another word. Or you apply C and D, for example, CD equals BC, then you get another word. If you apply to A and D, then you have DA. I can again make a commutation between C and D, and we get back this word, and there's no more other word. So we get a kind of equivalence class of word. For a given word, all the words you can obtain by making this commutation according to the relation C, which gives you the commutation relation. Okay? Then Cartier and Furata, in 1969, defined the commutation domain. This was in the lecture note, long time ago, and in French, problème combinatoire de commutation et de réarrangement. So it comes from some probabilistic or statistical property, which Furata and Estésis put in a completely commutable way, and then Cartier came and put this in a algebraic way. If you don't find this lecture note, you can find on the internet on the séminaire L'Interagien de combinatoire. This is the journal, electronic journal, and in 2006, if you go to this website, then you can get the monography in tech. It has been retyped in tech, and there is an appendix by different people for the development of this commutation model. So this is Cartier. Cartier show certain formula from the Grothendieck formula. This is a workflow institute in nobody understand this formula. And this is Furata. You see he's taking in left hand the infinite in his left hand. I have the mouse again. So you see, So bijection, there's no bijection in this class. I love bijective combinatorics, so the infinite, it's a famous point of infinite. I was very lucky to take this picture just. So I remind you, we go in a very elementary step, a monoid, it's when a certain set M is a product, the product is associative, and there is a neutral element. It's, yes.
No, just touch one of the keys, space bar.
We lost the laptop connection. But it's not there. It's not coming with it.
It's coming again, yes. So, very elementary definition of monoid. Of course, if you have some inverse, then you get a group. But here it will be only monoid. And example, natural examples, integer with addition, integer with multiplication. Here there will be a lot of free monoid. So the free monoid, what is a free monoid? You have an alphabet, A, of letters. The free monoid is just a set of words like this. And then A to AP is the element of the alphabet. And the product of two words is just a concatenation of the two words. You put one word and one AP, and B1, B2, BQ. It's a concatenation of the two words. And the neutral element is just the outer word. You want to know it at the top, nobody. And this will be the neutral element. So this is monoid. And now I define a commutation relation. Just a binary relation, C, which is symmetric and anti-reflexive. What means anti-reflexive? It's symmetric means if you have A in relation with B, then B is in relation with A. So if A and B commute, it's a symmetric relation. And it may be strange to say that it's anti-reflexive, that means A does not commute with A. Because it's a waste of time to commute A with itself. Do you understand when you go to RIPS that I need this convention that A is... And now I define the congruence. We have seen a class of words. So let's define the congruence. So relation C defines the congruence of the set of words of the free monoid. It's the congruence generated by the commutation AB equal BA. So two words are equivalent. If and only if you can go from one word to another word by making this commutation of adjacent letters according to the relation C. So we have seen before a word is 5 equivalent words. So this is an equivalence class of word. And I take the quotient of the free monoid by this relation. And the quotient is defined in the following way. So we take a word W. I denote by between brackets the equivalence class of the word for the commutation, and then the product with this commutation monoid, this quotient of the free monoid by the relation C, the product is defined by this. You take any representant V of a certain class, multiply by the class of V, and I define this as to be the class of the concatenation VV. And you can check very easily that this product of two classes does not depend on the choice of the representant of U and the representant V in each different class. So this is the commutation monoid. It's easy if you know, if you're an algebraist, you know this is easy. But I start slowly to not to lose everybody since the first lecture. So this monoid has been reintroduced in computer science. It was the name trace monoid. So trace is just an equivalent class of word. And this was a model for parallelism. The connection is that A and B, the letters, become some action. You are doing some action in a computer, in an same in an algorithm. And if you can do the two actions in parallel, means if you do A and then B, or B and A, it's the same result. If you can do the two actions in parallel at the same time, then AB equal BA. If you cannot do the two actions at the same time, the result depends. If you do A first and then B, or if you do B first and then A, the result is different, then means its relation, A and B does not commute. So this has been in theoretical computer science, in the language of theory. This has been a model with many papers, like Mazurkiewicz introduced this in 1977. It's a model for logical behavior of Petri net, but there are many papers in computer science, and we had a book in 1995, which is called the Book of Trace. So the many chapter in a language, in a theoretical computer science way, this Book of Trace. Now, second section, heaps of pieces. So this was introduced by your servitor, by the speaker in 85, so almost 30 years ago. So we have seen that from probabilistic result, like Sperre-Andersen principle, Fouata has done a collateral way to do this, then Cartier has done an algebraic way to do algebra commutation memory, and then I have done a geometric way to interpret equivalence class. And the geometric way is very visual. It's a spatial intuition, so this gives you a totally different intuition between the word up to commutation and this spatial geometric interpretation. So introduction to the heaps of pieces. Heaps of pieces is just a natural idea. Take a chessboard, put some, you see, some diamonds like this. A diamond is covering a black cell and a white cell. Suppose I put these diamonds in wood, and we put them one by one on the chessboard, so that the projection of the diamond in wood is exactly a black and a white cell consecutive. Imagine we put this one by one, and what you see, the picture, is the idea of the heaps of pieces. So another example is, you see there is some letter sigma 2, sigma 3, which correspond to each of the column. And this is this diamond. Diamond is connecting two lines in yellow. On the projection is two consecutive points. So this diamond fall down one by one. And the heaps is what you see now. Which means I forget in which order the diamonds fall down. For example, here and here, I don't know which one of these two fell before. But if I do this, then I know this one fell down before this, after this one. So this is not a heaps of pieces. You know, there is a game, Mikado, where you put some sticks, you put them all on the table, and you have to remove them one by one without moving the other one. So you cannot play, it's heaps of pieces, but also you can remove them one by one without touching or moving the other pieces. So this is a very intuitive idea, and it's surprising that there was no mathematical definition of this at that time. So here is a mathematical definition of the heaps, which be all over the class for 2 months. You will always you have to remember this main definition. So heap, first P for pieces, it's a set which I will call the basic pieces. Now C bolt is a binary relation on the set of basic pieces, which I will call dependency relation. In French, it's concurrency relation, but in English, it's not the same meaning. It's like a competitive relation when two elements are independent each other and in competition. And this relation is symmetric and reflexive. So if A is in relation B, then B is in relation with A, and symmetric with A is in relation with A. So we have these two things, and a heap. A heap is a finite set of pair. So it's pair alpha I. Alpha is a basic piece. It's an element of P. And I is any integer, positive integer, non-zero, non-negative integer. It can be 0, 1, 2. And I is called the level of the element. So this pair is called a piece of the heap. It's one of the elements of what we have seen before. So there is an element floating which is at a certain level, intuitively. The level is integer I, and alpha is a projection on the floor. The floor is it's a place for the basic pieces. I am going to give you some example of this. Satisfying condition 1 and 2. to have the intuition of these heaps of pieces. So this is the intuition, the basic pieces, when I have a heap of diners on a chessboard, the basic pieces were the projection of each of those diners. So the basic piece were a black cell and a white cell consecutive. That was the set of basic pieces. And now the heaps, any element of the heap, it's a certain diners. The projection is alpha on the chessboard, and I is a level at which I put these pieces. It can be level 0, 1, 2, 3. 0 is on the floor and any level. And there is two conditions, 1 and 2, to get the intuitive idea of heaps of pieces. So condition 1, if you have two elements of the heap at level I and j with a projection, I call this the projection, the first component, such that the projection alpha and beta satisfy the relation, the dependency relation C bolt. Then the level may be different. Intuitively, if you have two, say the pieces is this, if they are at the same level, they cannot be dependent. Dependency means they are going to hit each other. It's a second condition. If you have a piece, an element of the heap at level high, it's floating somewhere at the level I, then it does not fall down, the piece. So it means there is somebody at level I minus 1. And this somebody is a pair beta alpha A minus 1, such that alpha and beta are dependent. Each time you have a piece at level I, there is a piece at level I minus 1, so that the two projection alpha beta are dependent in the relation C volt. So that's the two only conditions we need. So this is the abstract definition of the heap. And we will see many examples. So P is a set of basic pieces, C bolt dependency relation. The element of the heap are alpha I. I call these pieces. The first element is the projection of the basic piece. Second element is the level, any integer. And we have these two conditions, 1 and 2. Example, heaps of segments. So you take the integer n. The basic piece are segment A and B, where you have any two integer A and B, and you take all the integer between A and B. So it is a segment A plus 1 and plus 2 until B. And the dependency relation is the following: two segments are in relation if and only if the intersection is non-empty. And with this, here is an example of the heaps of segments. So the first condition here, if you have two pieces at the same level, it's important if they are in concurrency, they cannot be at the same level. So which means, you see, if you have two segments at the same level, they cannot overlap. They cannot be in concurrency, in dependent, because the intersection should be non-empty. So which means that all your segments, it's a disjoint. They are all in this picture. All these pieces in red with the black balls are completely disjoint. So this is the first condition. The second condition, if you have a segment at level I, there must be somewhere a segment at level I minus 1. So that the two segments have a non-empty intersection. The two projections have a non-empty intersection. For example, this segment at level 4, and we have another segment at level 3. And if you take the projection, which gives basic pieces, this is the basic piece, and this is another basic piece. The two basic pieces in blue and green intersect. So this is the second condition. Any segment in this picture, you see this one, it's intersecting, the projection is intersecting with this one, or this one with projection intersecting, etc. This one and each one, you see it's at level I, at somebody below at level I minus 1. So in this class, there will be many special class of heaps of segments. There will be heaps of diners. A diner, you see, just two points connected at the same level and connected in consecutive vertical lines. So the projection, the basic piece is just a pair I plus 1, is the pair 2, 3, the pair 5, 6, etc. So more general example is if you take a set capital X, any set, and you take the basic piece, all the subset of X, or a certain family of subset, I will call this a basic piece, and then the dependency relation is two basic pieces, two subsets are dependent if and only if they have a non-empty intersection. So just take subset and you are going to make heaps of all these subsets. So for example, this sub-example, this heaps of diamonds, the set X, here we're just a chessboard, and the subset were just a white cell connected with a black cell, two consecutive cells, but you have to take the interior of this. This is a subset in real number, in the R cross R, but just take the interior of this subset. So that if you have two diamonds touching on an edge, they are not dependent. If you take the interior of this, then you have this idea of heaps of pieces which satisfy, you see, this picture satisfies exactly condition 1 and 2. Now, another example, you can, instead of putting diamonds on a chessboard, you can put hexagon, take the triangular lattice, like this, and an hexagon is a 6 triangle. So all the hexagons are not dependent. I take the interior of an hexagon and they are all disjoint interior. But I can make heaps of hexagons like this. You could make falling down hexagon instead of diamond and chessboard, and you see you have a hexagon falling, and what you see at the end, maybe you don't see very well because it's everything is in a projection. And at the end, you see what you see. It's you are looking above the heap, and you see there's only one hexagon in full size. All the other hexagons are hidden by another hexagon. And we will call this pyramid, this is in French, hexagon pyramid. And this will be very important for physics. So the physicist in the room, and this will interpret the gas density for certain, the hard hexagonal model. So you don't see the pyramid, but here you have a better view of the pyramid of hexagon.
Is there an easy way of enumerating them on the computer?
Well, there is some people try, but it's very difficult because there is an open problem with this. If you know what is a generating function, how many such heaps, pyramid of hexagon is n hexagon, up to translation. If you take one hexagon, there is 1. If you take two hexagons, there is 7 possibilities. You put the two hexagons one over another, or you put them overlapping by 2 triangles. Then I think there is 42 with 3 hexagons. But the generating function is very important in physics. It's a hard hexagonal solution model, and it's an algebraic generating function. If you know what is algebraic generating function, and this is an open problem to find a direct proof of this without using all the detours through statistical mechanics. But if you don't like pieces with a real number, hard hexagon in wood, then you can make discrete hexagon. See, here my hexagon, I am on the diagonal lattice. Hexagon has 6 vertices. And again, if the concurrence, the dependency relation is 2 hexagons overlap by 2 points or by 6 points. And you can feel that the heaps, if you take heaps of such a thing, it's isomorphic to the heaps of real hard hexagon wood. If you take real number. So you can feel that there is two different heaps which are isomorphic. There is some kind of isomorphism or morphism of heaps. We will see this later in the next week. Now we have seen that, so you take a set, you take subset of a set, and the concurrence, the dependency relation is, they are dependent if the two subsets intersect, but you can put a structure on the subset. For example, I have here a subset with integer -3, 2, 5, 7, -7, 9, and I define a cycle, like a cycle of a permutation, So I put a certain structure on my subset, and then I can define again dependency relation. So this is in French, concurrence, but dependency relation. So they are dependent if and only if. Two cycles will be dependent if and only if the underlying subset, the support, so the underlying vertices of the cycle are intersection is empty. So this is more another family of heaps. You have the subset, the complete dependency relation is a subset are intersecting, but you have a certain structure on the subset. Here a cycle. You can put heaps of groups, heaps of anything you want. As soon as you have a heaps of subset, then you can put some structure on the, and this structure is cycle, elementary cycle in the graph theory. It's an elementary circuit. It's a metatic cycle. It's a circular set of disjoint vertices up to a circular permutation. And this kind of cycle will be very important. Heaps of cycle will be all over the class. We will have a lot of heaps of cycle. So here is an example of heaps of cycle, you see, with a certain level. And you see this heaps of cycle, for example, this one is a projection, is in dependent set level I-1, and another one which is intersect, the projection intersect, they have a common vertex. So this is a picture of a heaps of cycle on the integer z. You take the integer z, you take subset of integer, and this subset you put cycle, and you can make heaps of cycle. So in general, the more general example, in fact, it's you have a graph. Below it's a certain graph, which I call the dependency graph. So the vertices are the set, all the black points are the set of basic pieces. There is an edge in green between two vertex if and only if they are dependent. So it is the relation C volt, the dependency relation. So you take any graph, and on this graph I am taking heaps of something on the graph. So you see for each vertex I put a vertical line like this, and on each of this line then there is some ball. This is the pieces of the heap. The red ball on each, I call it the fiber. Above the vertices there is many elements of the heap which project on one of the vertex of the graph. And now what is the condition 2? That if you have two red balls such as the projection, for example this one and this one, this ball and this ball, then the projection will be these two vertex, and they are dependent, so which means that the two red balls, they cannot be at the same level. So imagine the balls are big enough, more than half the radius, more than half of the length of this edge. They are big enough so that one ball is above another one. You cannot move the ball so that one ball is like this and the other like this. They are going to hit each other as soon as the projection of the ball are two vertex on the graph which are connected by an edge of the dependency relation. So you can imagine a heap like this, and you see this is a ball at level 0, this one is at level 1, this one level 2, this one level 3, level 4. So you can imagine the heaps. Very general. So in fact, the heap theory contains a graph theory. And we will see that there are many classical theorems on graph theory, like the chromatic polynomial, the cyclic orientation, and many different propositions, which can be reproved, revisited using heaps of pieces. So now heaps monoid. So we have seen the commutation monoid, we have seen the equivalence class of word, and I claim that an equivalence class of word is interpreted by the heaps of certain pieces. I'm going to define our product on the heap, which will be the heaps monoid. So to define this product, I have to introduce another notion, which will give me a second definition of heap. I have to introduce what I call a pre-heap. So a pre-heap is exactly the same as before. You have the set of basic pieces, P, you have the dependency relation, you have some pair alpha I, satisfying condition 1. So it's exactly the same, but I don't need the condition 2. So there is more freedom in your putting the pieces. So this is a pre-heap, you see. you don't say this segment is floating in the air. It's at level 5 and below there is nobody. So I call this for commodity a pre-heap. Now when you have a pre-heap, you can make elementary move. Suppose you have a piece, alpha high, at level I, and suppose you can move it, that is, you can delete this from the pre-heap and add this piece. So that is still condition 1 is satisfied. Or move it above or below. So I will call this elementary move. Example. See this piece, I can move it just below and does not hit anybody. So for the pre-heap, I can define as a pre-heap, or you can also move this one up. So for a certain pre-heap, you have many other pre-heap. So you have a certain equivalence relation. You can go from one pre-heap to another pre-heap by moving, by a lower move up or down of the pieces. And then there is a elementary lemma that everybody can admit without proof that in each, this is an equivalence relation in pre-heap. All the pre-heap you can get by moving the pieces such as the condition 1 is always satisfied. Then in each equivalence class, there is only one heap. Proof. So this is one element of the equivalence class, of the pre-heap, and then there is only one heap. Look. Okay, you have a pre-heap, and intuitively all pieces fall down, and each pieces in concurrence, in dependency of the other pieces, they touching level, integer level 0, level 1, level 2, level 3. And you can imagine if there were in hard wood these pieces with 1 centimeter width, and then they are going to fall down one over another, touching physically the pieces, like the diamonds of the chessboard or the hexagon of the pyramid. Or also you can, instead of making the gravity, you can put some helium in each of the pieces and everybody is going to be in the ceiling. So as soon as you define the ceiling, this will be the ceiling of the room, and all the pieces can go up. And you have an anti-heap or something. But all this is, so you feel this is the second definition of heap. It's equivalence class of pre-heap up to lowered elementary move, and the heap or helium heap, anti-heap is just a representant of this equivalence class. So I can define now a monoid on the set of heap. So again, I denote this heap's monoid by H for heap, P for the set of basic pieces, C the dependency relation, and I define the product of two heap. So example, suppose I have a certain heap of segment in red, and I'm going to define the product of this by this one. So if I put the two together, so they are going to overlap and to intersect, etc. I am going to take the product, to define the product of the red heap of segment by the blue heap. So the construction is the following: you put above all the blue. Take the blue, the second heap, this is E, this is F, take the second heap and put it high above the red one so that all the level of the blue are above, greater than all the level of the red. And once you have done this, then I am taking in the equivalence class of pre-heap, you take the unique representant of this blue, of the union. Now you take the union of the blue and the red. So this is the blue plus the red is a pre-heap. And I'm taking the unique heaps in this equivalence class of the pre-heap, which is a union of the blue and the red. So look carefully, I am taking the unique heaps, and this gives me a heaps of segment, which is exactly the product of the red heap by the blue heap. So this is the definition of the product internal heap. If I want to make a formalization of this definition, you have a certain heap in red, a certain heap in blue. The product of the two heaps is going to be the following. So you keep the heap here. Then T of F means the translation of F, but very high, so that all the level of the pieces in F are above all the level of the pieces in U. Then you take the union of these two, so which is, we satisfy condition 1, right, so pre-heap. And then you take in the equivalence class for the relation elementary move, you take the unique representant of this as a heap. So it's very intuitive. Once you have the spatial intuition of heap, it's a product of two heaps, it's just everybody falls down. The second heap is going to fall down on the first heap, but respecting the condition of dependency, and no PC is going to be broken by invasion of another piece. And then this definition gives you a monoid. It's, I am not going to be formal proof of it, but you can intuitively, if you have three heaps, it's going to be associative. I leave you the intuition. It's so intuitive that you don't need formal proof. And the neutral element is the empty heap. If there is no pieces at all, then it's a neutral element. So next section, now I claim that the two notions, commutation monoid and heaps monoid, are in fact isomorphic, they are in relation. I claim that a heap is just, for certain conditions of the relation, commutation and dependency relation, is just a geometric interpretation of the class of equivalent word. So proof. So I am going to prove that heaps monoid is isomorphic to a certain commutation monoid. So take a heap, with basic piece P, dependency relation 0, and then the basic piece at level 0, when it's on the floor, will be identified with alpha. So basic piece alpha 0 will be identified, a piece of this is a single heap with a one piece at level 0, I will identify with P the set of basic pieces. And then I am a morphism of monoid. If I take the free monoid generated by the basic piece P, which means it's a word, I take W is a word in a sequence of basic piece. The free monoid, it's a word, alpha 1, alpha 2, alpha n, where alpha I are just basic piece. And then I can make the product of this basic piece. When I identify this as a single heaps with a single pieces, I can make the product as a product of heap. Which means you are going to put the first pieces alpha 1, then the alpha 2 is going to fall down on alpha 1, alpha 3, etc. So maybe it will be separate, maybe it will fall down one over another. So you take the product of this basic piece, the product of heap from the first definition of the previous section. So it's a product of heaps with having a single piece. Each heap is a single piece, which is identified with the basic piece. So example. Let's take the word W equal alpha, beta, gamma, alpha, delta, where alpha, beta, gamma, delta are this basic piece. So the basic piece P, there is 4 basic pieces, which are subset. Alpha is a subset of a certain element with 3 elements. So take the set B, it was called capital X before. Take the set with 3 elements X, Y, Z. Then take some subset, the subset XY, the subset YZ, subset reduce a single element, the subset reduce a single element, and take this word. And take alpha, beta, gamma, alpha, delta, take the product of these letters, product as a product of heap. So first, put alpha. Then take the product with beta. Beta is a segment, is a dimension YZ, which is YZ is in dependency with alpha. So product beta is going to fall down on alpha. Beta will be at level 1. But make the product by gamma. Gamma is reduced to single point x. Now take the product with delta. Delta is z, so we have another alpha, and then delta. So you see I have this word, which is a product of basic piece. Each basic piece is a certain subset of my 3 element x, y, z, and what I get is a heap. And I claim that all the heaps are obtained from this world are exactly in bijection with the previous equivalence class of words I gave you at the beginning. So the concurrency, the dependency relation is alpha and beta have an element intersection, alpha and gamma have an element intersection, beta and delta have an element intersection. So this is a dependency relation between the basic piece alpha, beta, gamma, delta. Now you remember this picture? I claim that these are the 5 words giving the same heap. You can check that if you take all these words, these 5 words give the same heap, and these 5 words are exactly the 5 words of the beginning. When you replace each letter A, B, C, D by alpha, beta, gamma, delta, and when you replace now the commutation relation, here there is a commutation relation, C, A and B commute, B and C commute, C and D commute, and your commutation relation is exactly the complementary of the dependency relation. Which means that two letters commute. In fact, if and only if they are not in dependency, according to the concurrency relation. So C was anti-reflexive. Now C is a dependency relation, the complementary is reflexive. So you can see that why A doesn't commute with A, because A, in fact, is the worst case to be in dependency relation. When you have 2 subsets, they can be in dependency, it means they don't commute, but if you take the same subset, then they really don't commute. And they are really dependent, they are one over another, they touch completely each other. So you have this proposition now. So you have I repeat now what I have said in a formal way. So take this which goes from the free monoid generated by P, give you a certain heap. I define C, the commutation relation, to be the complementary of the dependency relation. And there is 2 lemma. Lemma 1, U and V, if U and V are equivalent for the commutation, if you can pass from one word to another one just by making commutation of adjacent letter, then the 2 heap will be the same. This is obvious, it's because suppose the pieces fall down one over another, when 2 pieces are not in dependency, then you can commute. If you put A and B, then it's the same as putting first B and then A. But you have the reverse is true. If 2 different words of the commutation monoid, 2 different words give you the same heap, then this word, you can go from one word to another word by just applying the commutation relation. So proof in the next section. So definition of the map phi bar. So you have the map phi is sending any word in basic piece in a certain heap. And now because of lemma 1 and lemma 2, you have a certain map from the commutation monoid. All the words up to commutation can be sent onto a heap. From lemma 1 and lemma 2, and then the proposition, this map is an isomorphism of monoid. So you see the connection is that you take condition monoid with letters of the basic piece. The commutation relation is just the complementary of the dependency relation. Another example with the heaps of diners. So heaps of diners will be important in all the classes. Is because if I take the basic piece diners, which is 2 consecutive integers, the dependency relation was 2 diners are dependent if and only if they intersect. So the complementary means I make now 2 diners commute if and only if I call sigma I to diner I plus 1, if and only if you have the distance between I and j is bigger or equal to 2. So sigma I does not commute with sigma I plus 1 or sigma I plus or sigma I minus 1, but sigma I and sigma j, I saw that the distance between I and j is bigger than 2, they commute. And if you have done a lot of algebra, for algebraist, you know the symmetry group, the Leckie algebra, Temporary algebra, braid algebra, there is braid group, there is many groups of algebra which are defined by generator and relation, and the generator are usually called like this, letters indexed by I, and the first relation is always this commutation, sigma I, sigma j, commute, if and only if the distance is bigger than 2. Or in Coxeter group, many algebra, so we will work. So this is the first representation of this equivalence class of world. It's a heaps. Then if you put more relation, like for the symmetry group, that means sigma I as inverse. So which means that maybe there is some blue. If you took 2 sigma I multiplied by sigma I, it should be the identity. So now if you take a diamond, put another diamond at the top, then they are going to collapse, to disappear. Sigma I to the square is going to be 1. And then there is a braid relation. So there is more relation, and this gives you permutation. But the first relation, the elementary step first is to take each of diamonds. So here is a world, sigma 1, sigma 2, sigma 4, sigma 1. If you like symmetry group, this can be the generator, the product of some transposition. Sigma I will be a transposition I plus 1, so you have a certain world. And sigma 1, so you see sigma 1, I take the product as a heaps of all these diamonds, so sigma 1, sigma 2, sigma 4, so 4 is 4, 5, sigma 1, sigma 4, sigma 3, sigma 0 is this, sigma 4. So you see, this word gives you these heaps, and now if you have 2 different words, I claim that these 2 different words, you can pass from one to another by commuting. So this is the blue, the red, the word gives you these heaps. And the blue one, it's a different word, gives you the same heap. So I claim that you can go from the blue word to the red word just by some commutation, elementary commutation between sigma I plus 1. So this picture, the heaps of diamonds, is a visualization of this word up to commutation. But this is 2 different approaches, 2 different points of view. In computer science, in trace monoid, you always work with word up to some commutation of letters. So there is some automata, if you are computer scientist, there is some automata which recognize language in the rational language, the Arabic language, etc. And there is some automata called asynchronous automata, which recognize the word of the trace monoid, which means it recognizes the word up to the commutation of the letter. If it recognizes one word, then it will recognize all the other words obtained by commutation. So the intuition is you read the word, it's a linear object. But here the intuition is a spatial intuition. You have heaps of pieces, and this is different intuition. So some people claim when I introduce this, but everything with same heaps, you can do it in the condition monoid with word. Okay, but you will see there will be some construction of heaps that is impossible to write it in terms of words. There is some geometric construction, very complicated, coming from physics, which explains some identities, but it's impossible to write this in words. It would be completely crazy to go through word. So this is 2 different intuitions. If you like word, you keep word. If you like geometry, space, you take hips. So this class is following a class I gave last year. But don't worry, the two classes are independent. You don't need to follow anything of the first class. So this class was last year a 24 hours class. This was an introduction to enumerative, algebraic, and bijective rhetorics. So it was, and there will be some overlap of the two classes. So I will need the generating function of the heap. So I will need to recall chapter 2 of this class. So I will remind you the notion of power series and generating function. I will need also the Catalan garden. There will be a lot of Catalan numbers in our history. So I will recall what we needed. And if you want to have more information, you can go to this website. And it's a website of the class where each classes have been videotaped. So you can see the video, you can see the slides. There is 2,000 slides of this class last year. And if there is an index, if you want to have a precise notion, you can click, go in the index, go in the chapter, and you click on the section you want, and you go to the video exactly at the good point. So you can go in the video like reading a book or going from one page to another. I will try to do the same for this class. There will be a website for the class with a different chapter and with section, and there will be up to 1 second, you will go exactly at the point of the video you want to see. So the content of the course, what we are going to do in this course, how can you speak 24 hours with heaps of pieces of commutation of letters which are very elementary notion? How is it possible? So you will learn a lot of things in this class. So first, this class will be in different parts. Everything, the first part, there will be 3 basic lemmas. 3 basic lemmas. Why I don't have the mouse again. 3 basic lemmas. So the first basic lemma will be I will make a formula for the generating function of heaps. If you take any heaps on a certain set, the total generating function, there will be a weight of the pieces, so the sum of the weight of all the pieces of all will be, there will be a generating function, I will explain what it is, and this generating function will be the inverse of another generating function which is D, and D will be the generating function of trivial heaps. Trivial means that all the pieces are at level 0. So in other words, to make heaps is equivalent to make inversion of something. And there is an extension of this inversion lemma where certain heaps with some condition, like to be a pyramid, for example, pyramid of 0, then the generating function will be a ratio of 2 numerator divided by denominator, where each of the generating function will be generating function of certain trivial heaps. Trivial, everybody is at level 0, there is no heaps at all. Second lemma, the logarithmic lemma, which tells you that the logarithm of the generating function of heaps is going to be the generating function of pyramid. To take pyramid, like we have seen, pyramid of the 1, roughly speaking, is to go to the logarithm. And now, third lemma, if you take a path, any sequence of points, any path, it's a sequence of points in any space, is going to be bijection with a heap of something. Heaps of cycle plus something on the top. And with these 3 lemma, we are going to prove 100 of beautiful things, completely different from one another. So this is the spirit of bijective rhetorics. At the beginning, there are many identities. Each identity you are going to prove this by a full calculus, everything, and then somebody becomes a beautiful bijection. I mean, the left-hand side is this and this, the right-hand side is this and this, and the interpretation of the identity is just to find a bijection, construction of bijection between the left-hand side and the right-hand side. Now there is so many identities, there is so many bijections, there's a whole jungle of bijection, identity, everything. So in this jungle, we are putting some order. Some bijection are all together in the same tool, what I call bijective tool. Bijective tool, like last year we have seen determinant. There are many determinants in combinatorics, which are explained by single lemma, with non-crossing paths. So many determinants come from this unique single tool with atomic calculus, bijective tool. So heaps of pieces are one of these tools. One of these bijective tools with 3 lemma, we can get 100 of different identities as soon as we put different heaps, different weight to all this. So this makes some order in the journal of bijection identities in combinatorics. And since the introduction of HIPS, there have been maybe hundreds of papers in different directions, which I will just mention here. So this is the map of the class. First, I will the first part, which maybe be 3 or 4 chapters or 5, will be basic definition and theorem. So we have seen the chapter 1, commutation basic definition. We have not finished with the first part. Then there will be a chapter 2 with 2 basic lemma, the generating function for HIPS and the logarithmic lemma. Then there will be a third chapter, HIPS, path, flow, monoid, and rearrangement. With a third basic lemma, path equal HIPS, and a modification of this third lemma, rearrangement equal HIPS of cycle. Now there will be some application to classical mathematics of all these 3 basic lemma. So we will have a chapter about HIPS and linear algebra. So all the classical proof, inversion theorem, Jacobi, all this classical, Keller-Milton, all this theorem will come from the 3 basic lemma in the HIP. With HIPS you can... now there is some strong connection between HIPS and orthogonal polynomial quantity fraction. So you don't need to know anything about quantity fraction, orthogonal polynomial, or linear algebra, or all this. I will reintroduce all this subject. So you will revisit some classical mathematics with this point of view of a tool of a 3 basic lemma unifying many things. And then we will go to graph theory with algebraic graph theory, chromatic polynomial, acyclic orientation, matching polynomial. We will prove some theorem just using again the elementary things and HIPS of PCs. Then we will have some application to theoretical physics. So don't be afraid, you don't need to know anything in physics. But this is some subjects which are very active in physics. Gas model in statistical mechanics and data animals. So this is a critical part. You don't need to know physics, but I will remind you the connection with physics. Then even there is some connection with quantum gravity. It's a very active field. In quantum gravity, you want to unify the 4 forces of the universe, so you want to unify quantum mechanics and general relativity, but we will work in 2-dimensional. The space-time will be 2-dimensional, so it's a very narrow space-time, 1-dimensional for the space, 1-dimensional for the time. Physicists introduce this Lorentzian triangulation, and then there is some identity, which can be very easily explained by going through HIPS of PCs. And then we will see QSL function in physics, polynomial, solid and solid model. All this also will be connected to HIPS of PCs. So we will learn a little of physics if you like to go outside the field of mathematics. Then there will be application to more advanced mathematics. So I will have no time maybe to go further, but I will explain what is the fully collective class of words in the first Coxeter group, which is a symmetric group. So there is a notion of fully commutative class, and this is everything explained with HIPS of PC. But this is even an active field of research because some people from other Coxeter group are using HIPS to find some new result on this. And this is related to algebra in physics. So temporary algebra, we will work on this, and everything we can clear with HIPS. And the dimension is a Catalan number of this algebra. And all this is related to rotation theory of linear algebra and operator on HIPS. There will be complementary topics. I will not maybe go to this level of the class, but maybe if some students want to pass an exam, maybe we can give some papers and they can explain. But for researcher, for professor, you have this connection with HIPS, and this is active research now. So this is some people doing some research. So the zeta function and graph and number series, you know the famous Riemann function has been extended to graph, and there is some, there is a book on the zeta function and graph, and some people are extending all this using HIPS of cycle. So a lot of things I explain, there is a strong connection on graph theory and HIPS of cycle. Now there is a book by Richard Green, and we have made 4 or 5 PhD students, where he uses, the whole book is about operator on HIPS, which give you a representation of what is called the Kac-Moody algebra. So you can have representation of these topics using, there is some operator on HIPS, you add an element, you delete an element, but this is deep and complicated. I will not go, but this is a strong connection with deep mathematics. Even very recently, dans notre note in Computer Science, he's publishing volume 1, 2, 3, now he's publishing volume 4, 4A, 4B, 4C, and he has published volume 4, fascicule 6. He just published it, and the sad problem is the satisfiability problem. It's a famous problem in computer science. And there is one fundamental lemma, and he has revisited it with heaps of pieces. He used a inversion theorem, N over D, to prove a probabilistic lemma. But he don't like the term heaps, because in computer science, when heaps is a data structure, so this colleague with the notion of heaps of pieces, he asked me to change the definition, but there is many hundreds of papers using heaps of pieces, you cannot change. So then finally he takes the word empilement, which is a French word. So in the Cloud book, you will see the French empilement de pièces. He's found it's a nice word, and some true French, like the jeu de taquin, in this case, the jeu de taquin in Unit Tableau, and now there is empilement in the computer science. So it's a very strong connection with the beautiful theorem, the Longueur theorem. So this is for people working in computer science. And in statistical physics, everybody has heard of the Ising model. Ising model, there is 200 solutions, or 300 solutions, and there is another solution by a young student in Vancouver, where he gave another proof using again heaps of pieces, and I discovered recently that people in the theory that I don't understand, the string theory, it's a very in geotheory equivalence in Ram-Mogulan, there is a 70-page paper, and the main theorem is about one of the lemmas that heaps of cycle is equal to rearrangement, and he rediscovers the commutation memory and everything. So these three basic lemmas, you see, go to many papers. For example, I have listed red, blue. For example, the blue lemma is a logarithmic lemma. You can find it in linear algebra. There is a determinant of trace of Jacobi, the Jacobi function with a logarithm of something. Here, the gas model, there is a logarithm. And here, the zeta function of graphs, also there is a logarithm. Here is the Ising model for the term there is a logarithm. So all of the proof, when you need the logarithm, you go back to the logarithm or the Jacobi identity linear algebra. But in fact, this lemma, that logarithm of heaps, is equivalent to take a pyramid. It's a basic, it's a source of all this proposition. Now you do the logarithmic something, and you say, okay, this is, you prove this by Jacobi theorem, all this comes from the same source, which is the heaps, which is pyramid and heaps of pieces. In green, you see this is the lemma that pass equal heaps of cycles, so it is used here, everywhere. This is analog with heaps of cycle and rearrangement, and also, you see, this is in inversion theorem, so these three basic lemmas give you plenty of different applications, so maybe it will become classical.
One where nothing is
Yes, because this is more. Yes, nothing. This is deeper. No, it's much deeper because he uses his operator. Here he defines what is called full heap. Full heap, it's very packed. There is not too much room inside, and he uses operator and full heap. So it's they don't use. No, this is deep mathematics with some more than the three basic lemma. So I will not go in the class in. This would be the book, a beautiful book in Cambridge University Press. It would be a full class. It's a whole book on rotation of Lie algebra. So this was, so there was some confusion. I'm sorry because my software I use to make my website is maybe there is some compatibility problem with where I have the server in Montreal, and it was announced by this. If you click this and you will have capital C, so now the exact website are this one or this one. So it's exactly the same as you have done, as you have received in the mail, but your capital C you replace by your small c. If you type this, it will go here, which is the first page is the old website, and all the other pages are the new website. And if you click one of the new page, then the first page will disappear and you get the new page. So I don't understand very much what happened, but at least if you go here or here, it will. okay, maybe it's enough for today. I will stop and I will give you next week the proof with normal form, the proof of the fact that there is isomorphism between the two. Okay, thank you.
So if you're taking this course